Okay, so we talked already about 0 over 0 and infinity over infinity as two of our indeterminate forms. There are a whole bunch of them. We're not going to do all of them. We're just going to look at two others. And I'm going to talk briefly about a third, but not do an example, because these two are the most common. So for all the years I've been teaching calculus, I've never seen a problem on the AP test that didn't fit into one of those two categories. But of course, if I didn't show you any of the other categories, what would show up on the AP test? One of those other categories. So at least I can say I showed them to you. They're not that difficult because both of the examples I have take something complicated and turn it into one of those. And so if you understand how L'Hopital's works, then these two new methods are pretty easy if you can do a little bit of algebra. Okay? So again, refreshing L'Hopital's. Plug and chug. If you get an indeterminate form, then you apply L'Hopital's. If it's not an indeterminate form, if it doesn't fit into any of these four examples we talk about, then it's not a L'Hopital's problem. Okay? Just because you struggle on a limit problem doesn't mean you can take the derivative of the top and the bottom. It's got to fit into one of these. Okay, so before we get into the next one, let's talk about this. What is that equal to?
0.
Why?
Because it's going to eventually just get so big, it might as well be 0.
Is everybody in agreement? Okay, and again, we're talking about as the number of the denominator gets bigger and bigger, where the numerator stays the same, that denominator will get very big, and eventually, as it continues to get bigger and bigger, this will approach 0. Okay, so think of 1/2, 1/100th, 1/1,000,000th. Okay. What about the opposite of that? What happens when the denominator gets, and we're talking about limits again, I'm not asking you what does 1 over 0 equal, because we know that's undefined. What happens when the denominator gets very small? Oh. Infinity. Good. Okay. So our next indeterminate form will be 0 times infinity. I'll talk a little bit about it, I'll show you how to use it, and then I'll show you an example of how to apply it. That is an indeterminate form. And with a lot of these indeterminate forms, we could argue all day long. Well, why isn't infinity times 0 just 0? Because 0 times anything is 0. It's the same argument we had with 0 over 0. What's 0 over 0 equal? Well, it could be 1 because it's a number over itself. It could be 0 because the numerator is 0. It could be undefined because the denominator is equal to 0. But in that case, we're just spinning our wheels. That's why these are called indeterminate forms, because you can't determine what they are. Okay, so this is going to be based on something like this idea. Actually, you know what? I don't want that limit there. Let's just talk about this. If I have f of x times g of x, that's the same thing as f of x divided by 1 over g of x. Okay, so chew on that for a second and make sure you understand what I mean there. Because remember, dividing by a fraction is the same thing as multiplying by the reciprocal. So if I go from the bottom up, if I'm dividing by 1 over g of x, then I multiply by the reciprocal, which would be g of x, and we're back to where we started, f of x times g of x. Okay, does that make sense? Okay, yes? Good. If that makes sense, then this is an easy problem. Because all you need to do is decide which of the functions you're going to send to the bottom, and you're good to go. Okay. So let me show you what an example looks like here. Let's take this, shrink it down and put it up here. Why did that spin? There we go. Okay, let's do the limit as x approaches 0 of x squared times the natural log x. Now, even though I'm doing an example of 0 times infinity, don't just assume that that's what I'm doing. You still need to check it. If you plug in 0, you get 0 for x squared, and the natural log is equal to infinity. Right? If you're not sure, graph the natural log and you'll see what I'm talking about. Okay. So that is in fact 0 over infinity. Or sorry, 0 times infinity I meant. Okay, so 0 times infinity, which means it is an indeterminate form. We're not going to apply L'Hopital's here because I don't have a rational function. L'Hopital's applies to rational functions, so I have to turn it into a rational function. The question you have to decide then is which one do you want to send to the bottom? Do you want to send the x squared or do you want to send the natural log? I usually send the less complicated one to the bottom, but it doesn't matter, you can still solve it either way. Okay, so I'm going to rewrite this as the limit as x approaches 0 of the natural log of x over 1 over x squared. Now, common mistake here is people write that as a natural log of x over x squared. That's bad math. That's good math. All right, we good? Everybody understand how I did that? Good. Now I plug and chug again. Now I get infinity over 1 over 0, which we talked about already to be infinity. That makes me happy. Why is that? Why does that make me happy? Because now I can apply L'Hopital's rule. I forgot. What's the derivative of natural log of x?
It's just x prime over x.
Which is
1 over x.
1 over x. Okay, good. What's the derivative of 1 over x squared? Negative 2 over x cubed. I made a big jump there if you're not with me. That's x to the negative second, so the derivative would be negative 2 times x to the negative 3, which becomes that. I just like it in that form better. It's up to you. So
Why would it be to the negative second? Just because it's underneath?
I'm just doing this bit. Remember, it's not a quotient rule, it's just a derivative of the denominator. Okay, which means dividing by a fraction is the same thing as multiplying by its reciprocal. So this becomes the natural log as the limit as x approaches 0 of 1 over x times x cubed over negative 2. Put that in parentheses so it doesn't get mistaken as a minus. X approaches 0 of negative 1/2 x squared. I'm done with the algebra. Now I just plug and chug again. And sure enough, 0, done. So that last step in pink right here, let me circle that. This last step in pink is a standard L'Hopital's problem. I could give it to you as is, but the stuff above that was the manipulation we had to do to turn 0 times infinity into infinity over infinity. So all of this stuff is just plain old L'Hopital's. Questions? We're good? Excellent. One more example to show you. One more indeterminate form, and that is infinity minus infinity. Another one that you could argue about till you're blue in the face. Well, isn't that just 0? Because anything minus itself is 0. Right. So there's a reason why it's called an indeterminate form. We're not going to argue about it. The only thing we're going to do with this is, again, algebraic manipulation. I'll give you an example. It's easier to see this in action when you see the example that I have for you. What is the limit as x approaches 0 of 1 over e to the x minus 1 minus 1 over x? What's e to the 0? 1. 1 minus 1 is 0. That's 1 over 0 minus 1 over 0, which would be infinity over infinity. So we are into that situation. The only thing I'm going to do with this bad boy is find a common denominator and turn it into one fraction. Yes? Okay. Clean that bad boy up. X minus e to the x plus 1 over x times e to the x minus 1. Do not cancel those x's. Bad math. Plug in 0. It's negative 1 plus 1 is 0 on top. And the bottom is 0. Oh, yeah. Beautiful. L'Hopital's rule. Hello, Mr. Weber. How are you, sir?
Hey, L'Hopital's rule is great.
Oh, it's beautiful. Right? Yep. Big fan of L'Hopital's rule, that, Mr. Weber. Weirdo. Okay. So we're back to one of our originals. So let's keep going. L'Hopital's. And a quick refresher on how to take the derivative of e to the x. Some of you might recall, some of you might not. Limit as x approaches 0 of 1 minus e to the x. Ooh, product rule. E to the x minus 1 plus x times e to the x. Got a little aggressive on that line. Let's get rid of there. Okay. I think that's right. Yes? Plug und chug. 1 0 over 0. What do I do now?
Double derivative.
Do it again. This is fun.
It'd be fun to say.
Limit as x approaches 0 of negative e to the x over e to the x plus x e to the x plus e to the x. I think I did that correctly. That's e to the x. The one goes away. That's a product rule. Derivative of the second times the first plus derivative of first times the second. Oh boy. Not an indeterminate form. 0 is 1 plus 1 is 0. Oh, I got a number.
You got numbers. Let's go.
What if I would have gotten 0 over 0 again?
Triple derivative.
Do it again. And again. And again. But I'm not going to ask you to do any of those. Those would be crazy. If you have to do it more than 3 times, it's probably one of those cyclic problems that I talked about on Wednesday. And you would just stop and cry. Problems? Okay. There are other indeterminate forms that we're not going to talk about. We're going to play the odds here and guesstimate that you won't see any of these others. However, some of the other ones, if you're feeling all fancies in your pantsies, would be things like 0 to the 0 power, infinity to the 0 power, 1 to the infinity. This one really bothers me because why wouldn't that just be 1? But it's the same argument that we had with all the others. So those are 3 others that show up.
No, there's a valid point there.
Because that's 1 times 1 times 1 times 1 times 1 times 1 times. You get the idea.
But then couldn't you also add all those other ones up together and then it'd be 1 times like 3 million, therefore it'd be 3 million?
You're gonna hurt yourself. Don't go down that
Dominus
rabbit hole.
Prime. Dominus Prime.
Just stop. Just stop.
one more.
We'll talk about this on the bus ride back.
There you go. You've got 21 hours to talk about it.
Are you on my list? Mr. Edie?
Yes, sir.
Everybody.
Certainly. Okay, so let me finish.